local state discrimination tasks. So in usual state discrimination task, someone prepares a state with some probabilities. Say a girl can prepare a state row 1 with probability P1, a state row 2 with probability P2, or a state row 3 with probability P3. Then after preparing, it gives the state to another person. That person knows about the probabilities and the corresponding states. So the person knows this Px and rho x, but that person doesn't know about what exact state he or she has received. But he or she wants to know, so can measure the state, and depending on the outcome, he can guess about the state. So if the state is taken from an orthogonal set, then by doing measurement, you can always know about the state. For example, if it's one of the Bell states, then by measuring in this Bell basis, these are not written in normalization notation, so it's not normalized. So now by measuring in this basis, you can perfectly say which state you have received. So they can be distinguishable globally. But then comes the local state discrimination, where again the person prepares a state, but that state has more than one parts, and the person gives one part to one person and the other part to the other person, and those two persons receiving the state lives in two distant location, so they can only do local operations and local measurements on the states. And if they want to discriminate, they should depend on those local operations only. And but even if you can even classical communication can help you by giving some resource. So they can also use classical communication for discriminating. For example, if the states are like this 0 0 0 1 1 plus 1 minus, then if the first person measures in the 0 1 basis and tells the output to the second person, then depending on the output, the second person can decide what measurement should be done. So if the output is 0 in the first measurement, then the second person can do measurement in 0 1 basis. Similarly, if the output is 1, then the second person can measure in plus minus basics. So by doing so, using local operation plus classical communication, the two parties can perfectly distinguish between these states. But these states are not distinguishable using local operations only. So now here you see, like these Bell states cannot be distinguishable locally, but they can be distinguishable globally. And it's obvious that the things you can do globally may not be possible to do locally. So there is a difference between these local operation plus classical communication and global operation. And by seeing this difference, you can say if there is some non-locality within the states. For example, in this paper, they have shown if there are a set of orthogonal product states, even if it's product, you may not distinguish them perfectly. So here they have given some examples also. So until now, I have considered the situation that the receiver who's trying to discriminate the state has access to any possible measurement. But then in our case, we have considered that the receiver has access to a set of measurements only, and using those measurements, they want to distinguish. So in such a situation, we have shown that the incompatibility of the measurements accessible to the receivers can give some advantage in the discrimination tasks. So there can be two types of discrimination tasks, the minimum error discrimination and the unambiguous discrimination. So in the minimum error discrimination, you have the state, you measure them, and correspondingly you will get some output. Corresponding to every output, you guess something about the state. For example, if the state is output is M1, you say the state is row 1. If the output is M2, the state is row 2. If the output is M3, the state is row 3. You may not be always correct. So the motive is to minimize the possibility of incorrect answer. So for example, if you know the state is 0 or plus, you can measure in this 0 1 basis. And if you get output 1, you can surely say the state is plus. If you get the output as 0, you can still guess maybe the state is 0, but this can be a wrong answer, because even if the state is plus, there is a finite probability of getting 0 as output. So then comes the unambiguous discrimination, where again you use the state and measure the state and you have some outcomes, but you don't answer always depending on all outcomes. So for example, if you have M1 as output, you can say the state is rho 1. If the output is M2, the state is rho 2. And if the output is M3, you may not say anything. You can say, I don't know what's the state. So in this case, when you say an answer, the answer is surely correct, but there is a possibility that you may not say an answer. For example, here for M3. So in this example, you say, see, there are again two states 0 plus, and you are measuring on 0 1 basis. So when you get the 1 as output, you can surely say the state is plus. But when it's 0, as I said, there is a finite probability of getting 0 as well as plus. So when you get the output 0, you say, I don't know. So here in this case, there is a finite, the motive is to minimize the probability of saying nothing. So in our paper, and from now on, I will only discuss about the minimum error state discriminations. So that's all about state discrimination. Let's move to incompatible measurements. If a set of measurements mx can be measured simultaneously using a parent measurement g, then it is called that it forms a compatible set. Mathematically, the output of those measurements can be written in this form, that is in terms of a parent measurement g, where g lambdas are the output of this parent measurement g. So from this equation, you can see that if you have the measurement statistics of g and you know these probabilities, so then using this relation, you can find the measurement statistics of all the measurement mx. So that means you can do all the measurement mx through this parent measurement g. But if the measurements are not compatible, that is, if those measurements cannot be written in this form, then it's said to be incompatible measurements. You can again quantify incompatibility. So this is a robustness type of quantifier, which says that the minimum amount of noise you have to mix with the measurement so that the whole thing becomes compatible. So now I can write this whole thing in terms of this parent measurement g. And by noise, I mean another set of measurements. So this lambda is another set of measurement. And by amount of noise, I mean this R. So the robustness of incompatibility is the minimum value of R such that this thing becomes compatible, can be written in terms of any parent measurement G. And this minimization is taken over all possible R, lambda, G, and probability distributions. And as I said, by noise, I mean another set of measurements. So these lambdas are another measurements. So these lambdas will satisfy some trivial conditions. That is, it is positive, it sums up to identity, and so on. So you may think that since compatible measurements can be done simultaneously, so compatible measurements are more powerful, more useful. But actually, there has been found that there exists various state discrimination tasks where incompatible measurements provide advantage over compatible ones. So I'm going to show you some results in this direction. So before going into the detail, let me say what type of state discrimination task I'm talking about. So this is an example. Say there is a boy and a girl, and it's the boy's birthday. So the girl wants to give him some gift, but the girl is confused about what to gift. So the girl directly asks the boy, what do you want in your birthday? The boy says, okay, it's a difficult question, but I can give you some options. So you can give me a t-shirt or a watch or maybe a pair of shoes. So the girl selects some shirts, some watches, and some shoes, but the girl is still confused among them. So the girl randomly picks up an ensemble, and from that ensemble, the girl randomly picks up a gift and gives the gift to the boy. Now the boy obviously wants to know what gift he has received. Classically, it's trivial. You can just open the gift wrapper and you can see. But quantum mechanically, the task may not be that much easy. So the boy has some set of measurements using which the boy wants to find out what gift he has received. So now there are two options. Girl can tell about the ensemble, that is if it's a shirt or a watch, before doing the measurement. In that case, boy can choose among the measurement depending on the information, or the girl can tell about the ensemble after doing the measurement. In such a case, the boy can't decide among its measurements depending on that information, but at least the boy can finally decide about what gift he has received depending on that information of that ensemble. So correspondingly, you can define three probability of guessing the correct gift. This is the probability when you don't have the information of the ensemble at any point of time. This is the probability of correctly guessing when you have the information of the ensemble, that is if that is a shirt or a watch or a shoe, but you have it after doing the measurement, but before making any decision. And this is the probability of guessing when you have the information before doing the measurement. So you can choose from your measurements depending on those information. So obviously these probabilities will satisfy this order. In this paper, it has been shown that the optimal guessing probabilities, that is these two probabilities, are same if and only if there exists compatible optimal measurements for the receiver. So from here, you can say that if you get a probability for a pair of measurements such that it is greater than the optimal probability having post information, that is having information after the measurement, that is if you get some advantage from knowing the information of the ensemble from beforehand the measurement, you can say the pair of measurements are surely incompatible. So this relation can be defined as witness of incompatibility. This has been shown in this paper. Now, finally, actually, we have focused on this result. Here, the authors have focused on this ratio, where this PG is the probability of guessing when the available set of measurement is mx, and the information of the ensemble is known from beforehand the measurement. And PGC is the probability of guessing optimized over all compatible set of measurements, maximized over all compatible set of measurements. In this paper, the authors have shown that this ratio is upper bounded by 1 plus incompatibility of this set of measurements mx. And they have also shown that corresponding to every measurement m, there exists some discrimination protocol for which this equality can be reached. Now you can see this is a positive quantity. So the whole LHS part is a number greater than 1. So when I say that this equality can be reached, that means the numerator becomes greater than the denominator. And here in the denominator, we have maximized over all compatible measurements. So you can get an advantage by using incompatible measurements. So in that case, you will get a probability which is greater than any compatible measurement. Now, even the advantage is linearly proportional to the amount of incompatibility present in the set of measurements mx. So this is how much advantage you will get. Now, let's move to our result, that is incompatibility of local measurements and local state discrimination. In our work, we have considered a more complicated situation. Complicated not in terms of physics, but in terms of relationships. So here, the girl has two boyfriends, and the boyfriends are friends with each other. So now girl again wants to gift them. So the girl chooses a bipartite gift and gives one party to boy 1 and the other party to boy 2. No, boy 1 and boy 2 lives in two distant locations, so they can only use local operations or local operation plus classical communication. So by doing this, they want to know what gift they have received. So this is the comparison between the previous discrimination task and our task. So here in the previous task, the entire state has been given to someone. So that person who received the state can do measurement on the entire state. But in our case, since a parts of the entire state is given to the person, so they can't do global measurement on the entire state. They can only do measurements on their parts. They can use classical communication or they may not use classical communication. So our motive is to see if the incompatibility of these local measurements can give any advantage, and if we can find any difference between the global situation with this local situation. And if there is some difference, if that difference somehow implies any non-locality present in the task. So mathematically, we say that in Alice's lab, there is a set of ensembles E1, E2, E3. Alice chooses an ensemble EY with probability QY. From that ensemble, Alice chooses a state row 1, row 2, or row 3 with probability Q. So Alice chooses a state row B given the ensemble is Y with probability QB given Y. Alice gives one part of row BY to Bob 1 and the other part to Bob 2. And this is the discrimination task of first kind. In this first kind of discrimination task, we also say that Alice have given the information of Y to the Bobs. Now in the Bob's labs, Bob 1 and Bob 2 has set of measurements M1 into M3 and N1 into N3. These are the measurements available in Bob 1's lab and these are the measurements available in Bob 2's lab. Now since they have the information of Y, Bob 1 can choose a measurement from this set with some probability pk with the information of Y. Similarly, Bob 2 can choose a measurement NL with probability PL given the information of Y. Then the final probability of successfully getting a correct state is given by this, where this is the probability of choosing an ensemble. This is the probability of choosing a particular state from that ensemble. This is the probability of choosing a measurement from Bob 1. This is from Bob 2. And this is the probability of getting a particular outcome C and D when you have chosen the measurement MK and NL. And this is the probability of guessing the state B when you have the information of C, D, the outputs, and the information of the ensemble Y. In the discrimination of the second kind, we considered that the information of Y is not given to Bob 1 and Bob 2. So here, the only difference is Bob 1 and Bob 2 can choose the measurements arbitrarily, independent of the information of Y. So these probabilities are not conditional probabilities here. So again, the optimal probability, the guessing probability is this, where these probabilities are not dependent on the information of Y. So the quantities under interest is, this is the probability I am showing in the previous slide. Now you can maximize over all strategies, that is all probability distribution of choosing each measurements and finally guessing about the state. After maximizing, you get the maximum probability of discriminating the states using the measurements MK and NL. And in the state discrimination of the second kind, we not only maximize over these probabilities, over these strategies, but we also maximize over all possible compatible measurements. So the final probability which we get is the probability of discriminating the states, the maximum probability maximized over all possible compatible measurements and over all strategies. Now the quantities under interest are these two probabilities. We will then discuss about the ratios of these probabilities. Now, these are the probabilities corresponding to local operations. Similarly, you can define again the probability of guessing the correct states for local operation plus classical communication. So in this case, Bob1 does the first measurement, and then Bob1 tells about the output to Bob2, and then Bob2, depending on that output, decides on his measurements. We only use one way classical communication, so the Bob2's measurement is the final measurement. So here the everything is same in the expression, but the difference here is Bob2 chooses his measurement depending on the measurement of Bob1 and the output of that measurement. That is, this probability depends not only the information of Y, but also on K and C. This is for state discrimination of the first kind. So again, you can maximize it over all strategies to get the maximum probability of guessing the states using local operation plus one-way classical communication. This is the state discrimination of the second kind. Here again, we use the thing that Bob1 and Bob2 doesn't know about the information of Y. So the probability of choosing a measurement doesn't depend on Y, but still they use classical communication. So Bob2 chooses his measurement depending on the output of Bob1. So it depends on K and C. Again, we maximize these probabilities over all possible compatible measurements here. So here in this case, the probabilities under interest are this one and this one. So finally, we found these ratios of these probabilities. This is in case of local operations, and this is in case of local operation plus classical communication. And as you see, these probabilities are upper bounded by some function of Im and In. So what is Im and In? Im is the robustness of incompatibility, that is the amount of incompatibility of the set of measurements M, that is the measurements available to Bob1, and In is the incompatibility present in the set of measurements of Bob2, that is these N measurements. So just to recall, by incompatibility, I mean the minimum amount of noise you have to mix with the measurement so that it becomes compatible. So these ratios are upper bounded by a function of incompatibility. We have also shown that these inequalities can be reached for every measurements corresponding to a particular state discrimination task. So as you see, the RHS of these inequalities are same, though the LHS are different. So let us compare with the previous result. So we have considered local measurements MK and NL, and here Im and In are the incompatibility of the local measurements. It is the incompatibility of the set of measurements M, and this is the incompatibility of the set of measurements N. You can consider this as a global measurements of this type MK tensor NL. Then using the previous result, you can find that this ratio is upper bounded by 1 plus incompatibility of the global measurements of the form M tensor N. We have shown that actually this is equal to this. So actually the RHS of both the inequalities are same. So you may think that then what's the difference? What extra we can find from these relation if the RHS are same for both the inequalities? I can say that yes, for these ratios the RHS are same, but if you focus on the numerator, then the bound on the numerators has been improved. So here from this relation, you find the bound on Pi as this one, and using our relation, you will find the bound on Pi as this one. And as I said, this quantity is equal to 1 plus Im into 1 plus In. We use compatible local operations or maximum local operation plus classical communication. And as usual, global operation always has some extra power than the local operation. So the probability here will be greater than the probability here. So this is less than this one. So there is some improvement on the bound on the probability of guessing using incomputable measurements MK and NL. Now again, as I said, that corresponding to every MK and NL, you can have some state discrimination task for which these inequalities can be reached. And as you see, these RHs are equal. So for that optimal state discrimination task, these ratios become equal. That's why we say that there is no non-locality present for that optimal state discrimination task. Now by no non-locality present, I mean no non-locality present in these ratios. Obviously, the individual denominator and numerator may have differences, but when you take the ratios, the extra terms get cancelled out. So the whole things become same. So to conclude, incompatibility of quantum measurements known to be connected to quantum state discrimination. We made the same connection for local measurements. That is, we have considered local operations as well as local operation plus classical communication. But here again, I want to emphasize that by classical communication, I mean one-way classical communication. Bob 1 only tells about his measurement outcome to Bob 2, and Bob 2 does his measurement. But this thing doesn't goes on. Then we found that the local bound is better than the global one, and no non-locality is found in the optimal state discrimination task where these bounds can be reached. You can find more information about this work in this paper. So thank you.
So thank you for this wonderful talk. If anyone has some question, please ask.
Thank you for your talk. I have one question.
Yes.
Do you plan to consider decoherence in your calculations?
No. You mean when someone sends the state is decoherent?
It may be like depolarization, like effect, or depolarizing channel, amplitude dampening channel. So, and then you will see the impact on your bounds or calculations.
Yeah, that would be an interesting direction. But yes, in our case, we have considered the ideal situation that when Alice sends the state, it perfectly reaches to Bob 1 and Bob 2. So there is no noise present. So we have considered that ideal thing. In the previous results, also, the authors have considered the situation in a noiseless scenario. So actually, there haven't been, as far I know, there haven't been any work by considering the effect of noise. So that can be an interesting direction.
But those calculations may increase the complexity.
Yes, of course.
Yeah.
Yes.
And yeah. Maybe that is the reason they are not considering decoherence. Thank you.
Yeah, thank you.
Any more question? If not, then let's thanks again Connie Kersens for her wonderful talk. So we can move ahead now. So thank you, Connie Kersens.
Yeah, so have the sharing been stopped?
Yes. It has stopped. So our next speaker is Keshav Das Agarwal. So he is, can you share your screen?
Sure. One minute.
Yes, it is visible. Yeah, it's fine. So Let me introduce Keshav Das Agarwal. So he is currently a PhD student at HRI Allahabad, and his today's title of his talk is the detecting critical and exceptional points through dynamics in non-Hermitian system. So you can start now.
Thank you. I would first like to thank the organizers for organizing such an extensive conference and giving me the opportunity to present our group's work. So our recent work has been in the dynamics of non-Hermitian systems, and I'll start with what are the non-Hermitian systems and what are the motivations. Why do we study them? Then the spin models we look into, the different kinds of phase reduction, the IXY model with the KCR I'll introduce and show the results, and finally the conclusion. So I'll first start with the non-Hermitian systems. So in quantum mechanics, all the Hamiltonians we consider are Hermitian Hamiltonians, which helps us to correspond each eigenvalue to the energy of the physical system, and each orthonormal eigenvectors are distinguishable eigenstates. If the axiomatic definition of Hamiltonians to be Hermitian is removed, these two problems will arise, and I'll introduce how these problems are tackled in non-Hermitian mechanics. But first, let's see why are they interesting. In non-Hermitian systems, they define a class of system which are classically they can be seen as an optical gain and loss systems. Quantum mechanically, they have been shown as an effective description of open quantum systems. As in quantum mechanics, the closed system evolves unitarily, but a subsystem can evolve non-unitarily, and this evolution can be described as an effective description such that a non-Hermitian Hamiltonian is acting on the subsystem. So this is what is meant by effective description of open quantum systems and distributed systems. They also shows interesting physics like the role of anti-unitary symmetries like PT or RT. Here PT is parity time, where parity is exposed to minus x, and time reversal is t goes to minus t. So parity time symmetry or rotation time symmetry. Our work has been concerned with the rotation time symmetry, and I'll introduce RT symmetry. So the first effect of PT symmetry in non-Hermitian mechanics was shown by Carl Bender in 1998 PRL paper. And he shows that the system can have real eigenvalues, even though it's non-Hermitian. Non-Hermitian systems also show rich topological properties in which the energy gap can be either point gap or a line gap. And it also shows advantages in quantum information tasks, such as in metrology. In many, these are two of them, in metrologically, and in our group has shown that non-Hermitian gives advantage in charging quantum battery. There have been experimental verification and investigations that these models can be realized experimentally as an effective description of open quantum systems, or like through reservoir bath engineering. This was the motivation of why non-Hermitian quantum mechanics is interesting. So the non-Hermitian Hamiltonian can, even though it's non-Hermitian, it can have all the eigenvalues real. In this case, it's the unbroken phase, the Hamiltonian, because all the eigenvalues are real, and it can be symplectically through symmetry transformation. It can be transformed to a Hermitian Hamiltonian. So this is pseudo Hermitian. It's not Hermitian, but it can be transformed to a Hermitian Hamiltonian. Also, all the eigenvectors satisfy the Hamiltonian symmetry. That is, if Hamiltonians has the RT symmetry, so the eigenvectors will also have the RT symmetry. Whereas in the broken phase, the Hamiltonian is defective. What is meant by defective is So the number of independent eigenvectors is less than the dimension of the Hilbert space. That means that certain eigenvectors coalesce, that is for certain eigenvalues, there are two eigenvalues, but the number of is a degeneracy, but the number of eigenvectors is less than the degeneracy. So that means the Hamiltonian is defective. And this is the broken phase. And the eigenvectors break the symmetry, the one with the complex eigenvalues, and it has complex eigenvalues. So there's point to note that there is no order of eigenvalues in a complex plane because there's no definitive order in a complex plane. So there's no notion of a ground state in a broken phase. There is an unbroken phase. Since all the eigenvalues are real, we can give a notion of what's the ground state is with the minimum eigenvalue. So exceptional points are the points. So a Hamiltonian has parameter, let's say a magnetic field. So exceptional points are loci of the parameter which separate these two phases. So this is an IFI model which I introduced, but which I will introduce. So Zhang and Song have derived the exceptional point in this case in the previous work. So our model is for the dynamics of this model and its extensions. So let me go. This was the complex eigenvalues, how it was treated. Also, there's a problem of orthogonalization. So in a non-Hermitian Hamiltonian, we'll have two type of eigenvectors. One is the right eigenvector and one is the left eigenvector. In the Hermitian case, the right eigenvector and the left eigenvector will be complex conjugate of each other. But this is not true in the non-Hermitian case. So this is a right eigenstate, and if we see from the left side, it's a left eigenstate. So in Hermitian, the right eigenstates may not be orthonormal. So one way is to by hand normalize the states. This is the Dirac orthonormalization. Whereas since this equation holds that the left eigenstate is orthonormal to right eigenstate, we can define a new inner product such that all the dual vectors should be taken from the left eigenspace, whereas all the vectors should be taken from the right eigenspace. So in this case, we define a map from a complex conjugate of the right eigenvector, because in Hermitian case, we take complex conjugate of a right eigenvector as a dual vector. So we just map from complex conjugate of a right eigenvector to the left eigenvector, and this map is the biorthogonalization metric. And it should satisfy a property that it should be Hermitian, and it should satisfy this certain equation with the Hamiltonian. So in this inner product, the identity operator, instead of the Shire, which is right eigenstate and complex conjugate operator, it's now Shire. So one of the possible choice of the metric is this, where P is the matrix. Like when we diagonalize a Hamiltonian, we can construct a matrix P with columns as the eigenvectors. So this is the diagonalizing eigenvector. So biorthogonalization only works in a unbroken phase, because you can only diagonalize in the broken phase. It's not diagonalizable. So what is the RT symmetry? So RT is the R in the RT is rotation around each spin by pi/2 axis. So if there's a spin of n systems, each spin is rotated by pi/2 around the z axis, that is in the Bloch sphere. So x goes to y, that is sigma x operator goes to sigma y, and sigma y goes to minus sigma x. So this is the expression of the R, whereas the time reversal operator is a complex conjugation, and it's an antilinear operator. So that for all the operators, one should complex conjugate. So Hamiltonian is RT symmetric if it commutes with RT operator. It might not commute with R or T individually. So for that, one has to satisfy the condition that RH is H star R. This is what is meant Hamiltonian by RT symmetric. I'll move on to the spin models, which is first I'll tell about the IXY model, which is Random Sum Network, and the IXY model. So IXY model is just a complex extension of the XY model. There is in the XY, there's a real parameter gamma, which tells us about the anisotropy between the X and the Y direction. If it's a complex parameter, this is an RT-symmetric Hamiltonian, which I'll show in the IXY text complex. So here, one can notice if you take an H dagger is not equal to H bar. So, and in this model, there are two parameters. One is gamma, other is H prime by J, which is H, the magnetic field strength, relative magnetic field strength. So, whereas if one takes RT, so X and X operator, sigma X operator will go to sigma Y, and sigma Y will go to sigma X, and we'll get the IXY. If we act RT on this, we'll get the Hamiltonian back. Similarly, there's the IXY model where the magnetic fields are alternate, like it's H plus HA on odd sides, and H minus HA on odd sides and H plus HA on the even sides. So these two can be solved analytically by Jordan-Wigner transformation, then Fourier transformation, and complex polygon, which is a direct extension of how an XY model is solved, or any TXY model is solved. We also look into the models with Kaplan-Shikman-Etin-Aharoni interactions, and these interactions couple sigma X and sigma Y in the nearest neighbors. And this is also an RT-symmetric model. Now, this model has three parameters because there's additional KC interaction parameter K. This was first introduced as an effective description of a condensed matter system, of certain kind of condensed matter system by Kaplan and Shikman-Aharoni individually. And this has been experimentally observed in certain materials. We also look numerically in the IXYZ cases. So these are the exceptional point after diagonalizing and seeing after which value of parameters there will be all the eigenvalues are real. So this means if a magnetic field strength is greater than the corresponding HEP, the Hamiltonian is unbroken and all the eigenvalues are real. In IKCA case, we see a parameter dependence between K and gamma, which I'll come to when I discuss the XY case here. Now we first move to phase detection, which is the unbroken phase and the broken phases. So for this model, we look into the IXY, IATXY, and the IXYZ numerically. First, let me introduce the dynamical parameter we look into. So let's consider a transversalizing field, which people have studied very efficiently. And this has two phases. One is an antiferromagnetic phase, other is a paramagnetic phase. So there's a phase transition at relative magnetic field being unity. And this is called the critical line. So the quenching protocol is you start with a ground state in a paramagnetic phase, let's say in one of the phases, and then you evolve with a Hamiltonian. Let's say if you change the magnetic field very fast. So if you evolve with a different Hamiltonian, there will be non-trivial dynamics. And the parameter people look into is the Loschmidt echo, which is the distance between the evolved state and the final state. In the Hermitian case, the denominator of this equation is just 1. So Psi0 is the initial state, Psi-t is the evolved state after the quench for time. And people look into the rate function, which is the log of this. So there are two things, Loschmidt echo and the rate function. So, I'm sorry. Marcus Hale has showed that this rate function shows non-analyticity if the quenching is done, if the critical point is crossed while changing the magnetic field, whereas it's smooth if it is in the same phase. There is no critical line is crossed. So he showed that in Hermitian cases, one can detect if the critical line is crossed or not during the quench. So what about DQPT in non-Hermitian systems? And people have tried to look in the non-Hermitian system through different models, but they have started with a ground state of a Hermitian model. So what we do is look for ground state in the unbroken phase and try to see how the dynamics evolves. So from the Loschmidt echo, we show analytically that in the momentum space, if in the IXY case, that if the quenching is done from the unbroken phase to the unbroken phase, the Loschmidt echo is oscillatory, whereas if it is done from unbroken phase to a broken phase, it is polynomially saturating. So we look at two averages of a long time Loschmidt echo instead of the it's the time average, transient time average, which is initial time average up to a certain tau naught, and long time averages, which is the tail, what value is it saturating. So the this is average till some short time tau naught, and this is average from some short time, from some long time tau 1. And people have shown that this eta s in Hermitian cases detect quantum phase transitions in a variety of different systems, where even the rate function, the original rate function, fails to detect. So here are the results for the IXY case, which is the rate function. This is the profile of the rate function. Solid lines in the first figure corresponds to a quench in the broken phase. So one can see it's saturating, whereas in the unbroken phase, it's oscillating. We show that the steady state averages, the steady state rate function averages of this system shows non-analyticity at the first differential at the exceptional point. So we show that this, even though the non-Hermitian X1 that shows non-analyticity at the first differential, which is shown by Bajor and Dora, in IXY case, the long time average is not just the rate function, but the long time average of it can detect the equilibrium critical lines. This is in the thermodynamic limit because it's analytically solvable. Similarly, for the IATXY, the steady state average shows non-analyticity without any differential at the exceptional points for different values of gamma. And this is also in the thermodynamic, the value saturate at small n. So this is our thermodynamic limit. Whereas for IXY results, we see at a transient time average, because in the long time average, finite size effect dominates. So we look at the transient time average, one can still see that when the quenching is done in the broken phase, so in this case, now exceptional point is 1.128. So when the Loschmidt echo is still oscillatory, when the quench is done in the unbroken phase, which is the above 3 lines, whereas in the first figure, if the quenching is done in the unbroken from the unbroken to broken phase, it decays and there's a very strong finite size effect. So we look at the transient time average and we show that there is non-analyticity in the first differential, always at the exceptional point. Like the non-analyticity will be there at the exceptional point. So it's at least a necessary condition. Now we'll move to a second work, in which we look in the IXY case, which is much more interesting. So first of all, I'll show how it is an effective description of a open quantum system. So consider a chain of spins, which is each spin is connected to a local bar, which is the blue reservoir bar, and a non-local bar, which is, and two nearest neighbors are connected to a non-local bar, which is the red bar. So the evolution of this system will be determined by the GKLS master equation of this form. So the middle term of the RHS in this equation is the local bar, whereas the last term is the non-local bar. So we showed that this can be written as an effective description with a jump operator, which we ignore it. Like in the semi-classical limit, this jump operator is ignored, and the effective description now is a non-Hermitian description, whereas H effective is given by the H system minus a Liouvillean part, which gives the non-hermeticity of the system. So for RT symmetry, we choose specifically Q and R. This makes gamma and complex parameter. And in the IXY case, we found that And this can be shown as a non-Hermitian IXY-KCA model, which is HIKCA. Now, this model, when we do Fourier, Jordan-Wigner and Fourier and complex Galois, we find that eigenenergies have this dependence. So one can see if gamma is less than k. So both of the terms in the under root part are positive because gamma square minus k square will be negative and both of the terms will be positive. So eigenvalues are always real if gamma is less than k. So gamma is the non-Hermitian parameter, whereas k was a Hermiticity parameter, was a Hermitian interaction. So when Hermitian interaction dominates, the eigenvalues are real, which one should expect. Whereas if the non-Hermiticity parameter dominates, we have an exceptional point which directly corresponds to the factorization point of the Hermitian KCA model. So this is the band diagram of IXY KCA model, where H is from 0.6 to 1.4. So when in part A, where gamma is less than k, that is Hermitian interaction strengths dominate, we see that there is a metal to insulator transition. There's a gap to gapless phase. Whereas in C and D, we see that when non-Hermiticity parameter dominates, we see a complex parts which are denoted by the dotted lines. And we look at the entanglement in the ground state. We look at the entanglement and whether we show that it is able to detect the critical lines and the exceptional lines as well. So this is for k 0.75 and different H and gamma. The entanglement is between the nearest neighbor sites, and due to translation symmetry, we look at the first site in the entanglement between the first site and the second site. And the measure of entanglement here is a logarithmic negativity. So the red line here denotes the exceptional point. So there is a maximum, always a maximum of entanglement at the exceptional point, whereas the yellow line denotes the factorization point, where the entanglement is 0. So when gamma is less than k, that is gamma is from 0 to 0.75, in this case, the system is completely unbroken for all magnetic field strength. So we look at the Loschmidt echo and the entanglement. Loschmidt echo is this, and the rate function is the log of this. So we show, just like Wagner and Dora, that there is a DQPT, but this DQPT is not a necessary and sufficient condition to say the critical lines, and we can detect this DQPT for certain magnetic field strength. So let me discuss on the figure on the left, which in this case, the x-axis is the initial H0, where the ground state has been taken, and final evolution has been done with the magnetic field strength H1. So the quadrant 1 denotes when the quenching is done from H greater than 1 to H greater than 1. So that means no critical line has crossed. Similarly, quadrant 3 denotes where H less than 1 to H less than 1, where no critical line has crossed. Whereas quadrant 2 and 4 shows cases when critical lines have been crossed during the quenching. So we expect that 1, 2, and 4. 1, 2, and 4. Quadrant 1, there should be no DQPT. Quadrant 2 and 4, there should always be DQPT, which we see. And we also expect if a dynamic quantum phase transition detects detects the equilibrium cases, we also expect the quadrant 3 to not show any DQPT, whereas this is not the case. So again, in the non-Hermitian case also, this is only a necessary condition, not a sufficient one. So we see that for different gammas, this is not satisfied. We also look at the entanglement fluctuation and show that even though Loschmidt echo can't, but the entanglement fluctuations can detect that if the quenching has critical lines crossed, like if the critical lines are crossed or not. So if, let's say, in the figure with the blue line, we are quenching from a very large magnetic field to various different magnetic field, and we see a non-analyticity at the critical line. And if the case is reversed, we see a non-analyticity in the first differential of the entanglement fluctuations. So in summary, we show. So conclusion is we show that the time profile of the rate function and time averages of Loschmidt-Echo detects the exceptional point in non-Hermitian cases. Whereas in IXY model with KC interaction, there is a parameter space where it is completely unbroken and it has a critical line. This in this completely unbroken non-Hermitian case, the supposed to be exceptional point is still the factorization point because everything is real. And in completely unbroken phase, DQPT does not respect critical lines, whereas entanglement dynamics detects the critical lines. So this is the team: Ganesh, Aditi, Tanoy, and me. Thank you for listening to my presentations. I'm open to questions.
Thank you, Keshav, for this wonderful talk. If anyone has some question, please ask.
Hello, sir.
Hello.
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 Yeah, I have the question.
Yeah.
How can we understand the Hermitian and non-Hermitian system in our real life?
So Hermitian system are standard quantum mechanical systems, whereas non-Hermitian is like you have an access to a subsystem and it's evolving quantum mechanically. So the global evolution is still unitary, but you don't know what is acting on the parts you don't have access to. You know about you only have the information of a subsystem, and you see an evolution. This evolution due to connected, like now, then everything you don't have an access to is considered as a bath, as an environment. So you in non-Hermitian evolution, you see the effect of a of the bath, and this GKLS equation is notoriously hard to solve. So if one can map it to a Schrodinger equation, the normal Liouville evolution, but the trade-off is now your Hamiltonian is not Hermitian, but it's a non-Hermitian. So this is to look into the open quantum systems, but through the lens of the Schrodinger equation.
Okay, thank you.
I have one question and one
Sure.
clarification question. So, thank you for your talk. Which entanglement criteria you used to identify entanglement?
We look at the logarithmic negativity of the spin 1 and spin 2. The rest all is traced out system. So now, before before calculating the entanglement, everything else is traced out. So we look at a C2 cross C2 system. So we look, we could have also looked at concurrence, but we looked at the logarithmic negativity.
You mean von Neumann entropy?
No. So C2 cross C2 systems, there's a PPT criteria to and it has been shown that it is a necessary and sufficient conditions. So logarithmic negativity quantifies that criteria. Because the rho 1, 2 will be a mixed state because everything, the complete n spin sides will be a pure state, but just the rho 1, 2, if we trace out the rest of the system, this rho 1, 2 will be a mixed state. So you can't look into the von Neumann entanglement entropy because it's defined only for the pure states.
Could you please name the entanglement criteria you used? Name again.
The logarithmic negativity. Logarithmic negativity quantifies the PPT.
Okay. And
PPT says that. Sorry.
Please continue.
So PPT says that if the eigenvalue of a partial transpose is negative, it is entangled. Logarithmic negativity quantifies how much entangled.
Okay. PPT, what is the full form?
A partial positive transpose.
Okay. Thank you. Second clarification question. If I understood correctly, at exceptional points, there is maximum entanglement. Am I right?
Yes.
Okay. Thank you.
Any more question? So I think there is no question. So
Thank you
our,
for the opportunity.
yeah, once again, thank you. Thank you for this wonderful talk. So our morning session ends here, and our afternoon session will start at 3 p.m. So please join them.